common source amplifier configuration, which is shown in this figure. So to see the frequency dependence of the gain in common source amplifier, if you recall, up until now we have not included in the small signal models the coupling capacitors or the bypass capacitors, all the external capacitors which are there in the circuit for coupling and bypass. But besides those, we have the internal capacitances of the transistor as well, which are in the order of picofarads, or the junction capacitances and capacitances between the gate and the channel, gate, drain, etc. So up until now, if you recall, if you draw the AC equivalent circuit, well, it was something like this. So, without the capacitances, we have the signal. Okay, we have the signal source, V signal. So we are going to draw the small signal model again. So let's recall what we have discussed previously. So then we have the signal source resistance, output source resistance R signal, and with that the coupling capacitor CC1, we took it as a short circuit. Okay, but then it turns out that the coupling capacitors, which are usually of the order of microfarads, they are not. I mean, you cannot treat the capacitive reactance as a short. For very low frequencies, the capacitive reactance is large, and then you cannot treat them as short circuits. So, but just to concretize our understanding with previous circuits, let's first of all neglect those capacitances in the small signal model to see just to drive the circuit without the capacitances and find what is the mid-band gain. Okay, that is the gain without frequency dependence. So we have R signal, then we have RG, okay, the resistance, the biasing resistance at the gate of the transistors, of the MOSFET. So this is the gate terminal, okay. And then between the gate and the MOSFET, gate and the channel, there's a loss. The capacitance, the gate to channel capacitance is also neglected, and we assume that the input impedance or the resistance of the MOSFET is very high. So there's nothing over here. So at the drain terminal where you're taking the output, well, you're going to have a current source, a dependent current source, which models the source current, source to drain current of the MOSFET. It's given by the transconductance gain GM in terms of GM VGS. Okay, so this is GM, the transconductance gain, which is purely determined in terms of the quiescent drain current and the conduction parameters given by 2 square root of IDKN, if you recall. So it's GM, VGS. Okay, these are the small signal quantities, AC quantities. So then this is the source terminal. So I can write this node, this source, which is grounded. Okay, you can see this bypass capacitor. If you're taking this as a short, and then just forget about this independent current source, which is biasing the transistors in the saturation region. If it has to operate as a linear amplifier, okay, then this current is biasing your transistor into saturation, okay, without the need of the biasing resistance. This independent current source is doing the job. So you can kill all the DC sources, and then if you have a finite channel with modulation parameter lambda, then you have the internal resistance R0, okay, at the drain, between drain and source, okay, that's given by 1 over lambda IDQ in terms of the quiescent drain current. So that R0 and GM are the parameters. These are the small signal parameters which are evaluated in terms of the DC quantities like drain current and the quiescent point of the operating point of the transistors. Okay, and then again, if CC2 is short, so you're left with 3 resistances. So one is the load resistance, and the other is the drain resistance. Okay, because the drain you're killing that VDD source. So okay, you'll have RD in parallel with RL. Okay, so now let's have another resistance. That's it. This is your AC equivalent circuit, or including the small signal model of the MOSFET. So this is the drain terminal, and the output is being taken out from the drain node of the MOSFET. Okay, so this is V0, and this resistance is RL. Okay, so 3 resistance. We have the combination of 3 resistances in parallel. So it's very easy to see without the dependence of frequency. You can write the gain of the transistor AM as well. will be minus GM, well, before the gain, you could write the output voltage V0 as minus GM VGS. That's the AC voltage between the gate and source. Okay. Then a parallel combination of all three resistances R0 parallel RD to RL. Okay. So you see the output voltage does not has any depends on the frequency, because we are not including the effect of capacitances. So this is what we have discussed so far. Okay. And well, if you can express VGS in terms of the signal, you can derive the gain. Okay, again independent of the frequency. So you can see over here the voltage at this terminal can be given by the voltage division between RG and R signal. And well, since the source is at ground potential, we can write VGS as RG divided by R signal plus RG. Okay, R signal plus RG, and multiply by the signal source, that is your V signal. Okay, and if you plug this expression of VGS in terms of V signal into V0, you can derive the voltage gain. So if I write the voltage gain AV as, I can express this as in terms of V0, the output voltage divided by the input voltage, that is the V signal. This becomes, expression becomes, you're combining the first two equations, you can see this can be written as minus GM, I think this is GM, minus GM R0 parallel RD parallel RL multiplied by the voltage divider, which is present at the input, so that is RG over R signal plus RG. Okay, R signal plus RG. If you see if the output resistance of the source R signal is small compared to the biasing resistance of RG, then you can neglect this ratio. Okay, this becomes unity. Okay, so all we have done is we plug this VGS over here. Okay, and we have brought V signal, so it becomes then you can find the ratio of the output voltage to the input voltage, and you can end up in this expression, which is independent of frequency. So I'm not putting any dependence of frequency. So the voltage gain is not a function of frequency. You can easily say that this voltage gain is the mid-band gain. That's the band, or the bandwidth. That's the gain in the bandwidth of the part of the frequencies in the frequency response of CS amplifier, where there's no dependence of frequency. Okay, in the designing of amplifiers, when it is operating as a linear amplifier, you must know that usually such amplifiers have a very large gain bandwidth product, and you will come across this term. We'll talk about this gain bandwidth product, but before that, you have a very large 3 dB bandwidth. Okay, 3 dB bandwidth is where your gain is within the 3 dBs of maximum. Okay, and that's the value where it's not depending on frequency. So for most of the application, this should be the case. This is the gain which is to be considered in the designing of amplifier. But then again, if your frequencies are low enough or very high, you have to take into the consideration the effect of the external capacitances as well as the internal capacitances. So to understand the dependence of the gain of MOSFET amplifier on the frequency of the input signal, let's consider the common source CS configuration shown below. This configuration is without capacitances again. So this is the point. Up until this point, this is what we have discussed. Derived small signal parameters. So let's go ahead and include some capacitances now. So you see, when the circuit of common source MOSFET amplifier was studied before, it was assumed that the coupling capacitors CC1, CC2, and the bypass capacitor C. So these are the coupling capacitors CC1, CC2, and then you have the bypass capacitor CS. They were acting as perfect short circuits at all signal frequencies of interest. Now we also neglected the internal capacitances of MOSFETs, that is the capacitance between the gate and source and drain terminals. So CGS and CGD of MOSFET amplifier are assumed to be sufficiently small to act as open circuits at all signal frequencies of interest. So as a result of ignoring all the capacitive effects, the gain expression was derived was independent of the frequency. So in reality, however, this situation applies only over a limited, though normally wide band of frequencies. Okay? Usually the bandwidth is large, so the gain, this gain, the midband gain holds for a very large bandwidth operation of the amplifier. This is illustrated in the figure below, which is the sketch of the magnitude over the overall voltage gain, AV of the CS amplifier versus frequency. Okay, so this is the magnitude of the voltage gain AV given as the ratio of output voltage by signal versus the frequency, okay, in hertz. So you see between, and this is the bandwidth, this is the 3 dB bandwidth operation where the midband gain is within the 3 decibels of the AM, which is the midband gain. Midband gain is where you can neglect all the capacitances, okay, so that should be considered for the design of linear amplifiers. So this is the gain which is to be targeted, okay, for certain applications like audio applications. The range of frequencies should be such that it should fall in the midband gain within 3 dB, for example, where you have a constant gain which is not dependent on the frequency. Okay, otherwise the capacitive effects they take over and they can reduce your gain, which is not intended. Okay, so we observe that the gain is almost constant over a wide frequency band. This is called the midband. So this is the midband. So the value of the midband gain corresponds to the overall voltage gain AV derived before without circuit capacitances. So this is what we've derived over here, and the same expression. And this expression has no dependence on the frequency. It's just in terms of the circuit components and the transconductance gain of the MOSFET GM. You see what happens. So there are 2 points we have already talked before about, not over here. This is FL. So then we have another point. Let's not consider this point. Then we have another point, that is FH. The difference of these two frequencies is the 3 dB bandwidth. Why? Because at this point exactly the response falls to 3 dB. If this is 0 dBs, then this point, these 2 points, they correspond to minus 3 dB of the gain. Okay, that's where the gain response falls to 3 dB down of the midband gain. And in the low frequency range, the low frequency band, the gain falls off. The effect in this range is due to the external capacitances CC2, CC1, and the bypass capacitor. Okay, these capacitors are usually in the range of microfarads. So these are not as small capacitances as compared to the internal capacitance, the transistors, which are in the order of picofarads. Okay. So what happens is that at low frequencies, these capacitances are in microfarads. At low frequencies, the capacitive reactance is large, so you cannot treat them as short circuits. Okay, so therefore the dependence on gain on the capacitance comes into the picture, and the gain drops as the frequency becomes small. Okay. Similarly, for the small capacitance, internal capacitance at high frequencies above FH. These capacitance cannot be treated as open circuit components, and they start to show their effect in the frequency response, so where the gain starts dropping off, and these capacitances they start acting as short circuits. Okay, so you cannot treat them as open circuits above FH. So the frequency response shows that a gain falls off at signal frequencies below and above the midband. The gain falls off in the low frequency band. That's due to the fact that both, even though the coupling capacitances and the bypass capacitors are in microfarad range, so as the signal frequency is reduced, their impedance is increased. So they are no longer behaving as short circuits. So in this circuit, we cannot keep them as short circuits, but what we have shown over here in this equivalent circuit, because at low frequencies, their impedances are not small. Okay. So if signal frequency is over here is small, we have to include in this for the small signal response for the low frequency response of common source amplifier, we have to include in your small signal model the coupling capacitances and the bypass capacitances. So on the other hand, the gain falls off again in the high frequency band as a result of the internal capacitances, gate source, and the gate drain, which though very small in the order of picofarads or fraction of picofarad for discrete devices and much lower for IC devices. Their impedances at high frequencies they decrease, and thus can no longer be considered as open circuit. Okay, so as the frequency is increasing, the capacitive reactance given by XC, which is 1 over omega c. Well, you cannot treat them as open circuits. They're short. They become short circuits, and therefore start affecting the voltage gain at above FH. Okay. So the midband is obviously the useful frequency band of amplifier. Usually FL and FH are the frequencies at which the gain drops by 3 dB below its value at the midband. Okay. So the amplifier bandwidth or the 3 dB bandwidth is defined as the difference between the lower and the upper frequency FL and FH. So the bandwidth is FH minus FL. That's a 3 dB bandwidth. That's where you can treat the response of the voltage gain response as independent of frequency, almost independent of frequencies. Given FH is much greater than FL for a very large midband gain of for a very large midband bandwidth of an amplifier, you can treat the bandwidth as approximately equal to FH. Okay, since FL is small compared to FH. A figure of merit usually used for the amplifier is the gain bandwidth product, which is defined as the multiplication of the magnitude of the midband gain and the bandwidth. Okay, so it will be shown at a later stage that in the amplifier design, it is usually you can trade off the gain or bandwidth. For example, if you recall, in our earlier discussion, we used our source resistance. If you use a source resistance at the source point, so for example, if I employ a source resistance over here, okay, there is a Vs. So this source resistance, it tends to, so if you exclude this current source, use the source resistance. This source resistance tends to stabilize the Q point somehow. I mean, owing to the variations of the physical parameters like temperature that changes the conduction parameter of the MOSFET. RS can stabilize the changes in the conduction parameter. It can stabilize the Q point against such variations. Okay, but it can reduce the gain at the same time. RS means loss. You are introducing loss in the circuit. Therefore, if you, for example, the expression for the voltage gain for this kind of an amplifier implying the source resistance will be of the form minus GM multiplied by RD, RL, okay, R naught, and well, if R naught is huge, well, you can ignore its effect. Anyways, so divided by okay, so this will be of the form 1 plus GM RS. Okay, that means the gain is small. This gain is reduced because of the inclusion of the source resistance. This might has an advantage of stabilizing the circuit, that stabilizes the Q point of the circuit, but it tends to reduce the gain. It tends to reduce the gain with RS. On the other hand, it can improve the bandwidth. Okay, so you can always trade off the gain for the bandwidth. So one way to accomplish this, for instance, is by adding the source resistance, source degeneration resistance RS. Okay. All right. Now let's have a look at the high frequency response. High frequency response means we are interested in this band where above FH, what is going on in the circuit, to model the effects of the to see how the gain is being affected by the internal capacitances of the MOSFET device. We have to include the effect. So the gain, since in the high frequency band, the gain falls off due to the effect of the internal MOSFET capacitances, CGS, CGD. So we have to redraw the circuit, and we have to include those capacitances in the equivalent circuit model. So this was the equivalent circuit model. Let's go ahead and include those capacitances. Okay, so for example, over here we are going to have CGD. Okay, so we are going to have CGD over here, which is very much, you will see in the equivalent capacitance of common source amplifier. It's very much prominent in establishing the which will dictate the frequency response fall off after FH. So CGD is there. What else is there? Well, we can have CDB as well, but I mean between a drain and source, CDS or CDB. CBS will be 0. Okay, so let's take CBS, which is, since the body and the source is the same node. Okay, they're both the body and the bulk of the semiconductor substrate and the source are tied up together. So CBS is going to be 0. We're not going to consider that. Okay, and also CDB. We are going CDB is approximately, you can take it 0 as well, just to CDB or CDS between the drain and source capacitance, just to ease the analysis. Okay, its effect is not going to be, I mean, we are not going to consider its effect in our analysis. Okay, and so what we are left with is third resistance, which you can see over here. So we have CGS. So we'll have CGS. Okay, so between gate and source there will be another capacitance coming up. This will be CGS. So these capacitances are going to affect your frequency response after FH. So for the frequencies greater than FH, you have to consider these capacitances, the gate capacitances between gate and drain, gate and source. Okay, but however the gate and body, we okay, I mean gate and body, that's again the CGS. Okay, but between the body and the source, that's 0. Okay, we don't need to consider that capacitance because the terminals are shorted out. And CDB for analysis for easy, or CDS is not being considered. Okay, to ease the analysis. Otherwise you will have another capacitance over here between CDS. Okay, so we are not going to consider this capacitance. So let's not take this into the account. Okay, so to determine the frequency response, we will have CGS. We're going to have CGD. Okay, no CDS over here. You can see. Otherwise, the model is the same. Okay, that we have seen previously. So we have just included two lumped components. That is the capacitance between the gain and drain, and then gain and source capacitances. So we determine the gain or the transfer function of the amplifier of the common source configuration shown below at high frequencies. We have to include those capacitances, and particularly upper 3 dB frequency FH, we replaced the MOSFET with high frequency model. So this is the high frequency model. Okay, this is the high frequency model where you're including the internal capacitances, and these internal capacitances are responsible for the fall off of the voltage gain after FH. So this model is valid for frequencies greater than FH. Okay, FH is again the 3 dB frequency after which the response falls off due to those capacitances. So at these frequencies, CC1, CC2, the coupling capacitor, the bypass capacitor in this figure, they can be taken as short. Okay, because the frequency is high, so they will be behaving as perfect short circuits. Okay, I mean this X, CC1, 2, and S, this all equal to 0. This is 1 over omega C, and this can be CC1, CC2, for example. Okay, for CC1, since omega is approaches to infinity, it's very large. So we are going to treat them as short circuits. Okay, 0 impedance. So we don't have any coupling capacitances, bypass capacitances. We just have the internal capacitances of the MOSFET in the figure. Okay, so the small signal equivalent circuit can be simplified by utilizing the Thevenin theorem at the input side and by combining the 3 parallel resistances on the output side. So the resulting simplified circuit is shown below. So from this, how you reduce this circuit to the circuit on the reduce the left hand side circuit to the right hand side is that you can, first of all, you can combine these 3 parallel resistances into one resistance. So this is RL prime given by R0 parallel RD parallel RL. Okay, and then what you do is you have the voltage division. Okay, so by applying the voltage divider over here at this node, you have this as RG. This will be RG over RG plus R signal into V signal. So that's the voltage available at the gate of the AC. The AC VGS becomes this is AC VGS. This is the voltage between the gate and source. Source is at 0, so this is the AC voltage available at the gate of the MOSFET. So VGS is RG over RG plus R signal, V signal. Okay, and then these two on the input side, these two resistances, they come in parallel. So you have R signal prime as R signal parallel RG. And normally we RG is much greater than R signal, so this can be taken as RG itself. Okay, and RG is much larger. then this is simply R signal, then approximation, this will be an R signal only. So this is a simplified version, okay? So you have reduced the resistances in the circuit. Otherwise, other than that, there's no change, okay? So the circuit can be further simplified if we can find a way to deal with the bridging the capacitor CGD that connects the output node to the input side. So the output node, this is the output node where we are taking the V naught. So if we can bridge this to this capacitor is bridging the, basically this is the input node and the output node. So let's find a way to how to simplify this. So what simplification are we looking at is that can we have for example looking from this side towards the output, can we have an equivalent capacitance that can come up over here, okay, and then it will be easy. So it will be just I mean, if we can draw a circuit, so if we have an equivalent circuit, equivalent capacitance over here, then what we have is a single pole RC circuit, a low pass circuit of this form, okay, at the input side. So we can write the transfer function in the form of well, the form of this will be 1 over let's say a constant over 1 plus S times omega, okay. I mean, this omega is also the time constant of the circuit in terms of RC equivalent. So if we have this as equivalent, and this is omega is 1 over RC equivalent, okay. So this takes the low form. So we know the transfer function of this circuit, okay. So this is the resistance, and then we can combine C equivalent with CGS, okay, to form a single pole RC circuit. So we can develop a very simple transfer function for that. So towards that end, consider the first the output node. So let's talk about this node, okay, this node. So it can be seen that the load current is GMVGS minus IGT. So the load current which is entering this branch is the difference of this current GMVGS, which is the source current, source to drain current of the MOSFET. The difference of this current minus the current that is coming into the output node. So the difference of these two currents is what we have in this branch, okay. So it's IGT, so it's GMVGS minus IGT, where GMVGS is the output current of the transistor and IGT is the current supplied to very small capacitance, through very small capacitance CGT. So at frequencies in the vicinity of FH, so if you have a small frequency, I mean the frequency is not large enough, it's in the vicinity of the 3 dB frequency FH, that means, so which defines the edge of the midband, and that's the point where you can neglect this capacitance, okay. So if you can neglect this capacitance, then IGD is very small current, and then you're left with GMVGS only. So GMVGS is the only current that will flow in the RL. So at the vicinity of at frequencies close to FH, it is reasonable to assume that IGD is still much smaller than VGS, GMVGS, and with the result that V naught can be given approximately by, so this is around FH, okay, this is when the frequencies are around FH, so this is GMVGS into RL prime, where RL prime is the combination of 3 parallel resistances, okay. So over here, you can write this RL prime, if you want to expand this is how it is. But again, these expressions are close to FH. So this is the output of the circuit, close to the mid-band band, which is FH is 3 dB frequency. Okay. So since V naught is VDS, okay, V naught you can see over here. This is the drain terminal, right? I mean, this terminal is the drain terminal. This is the drain. Sorry, this is the drain node. This is the drain node of the MOSFET. So this can be written as VDS as well, because your source over here is 0. Source node is set to 0. So this V naught equal to VDS is the gain from gate to drain. Okay, so this we are considering the gain from gate to drain. If we are going to consider VDS or V naught, this is the same. So that's also the gain. So okay, if I'm going to write this as VDS, then around FH, this also becomes the gain of this is the gain at the drain node from the gate terminal only. Okay, it's not the small signal gain, it's just between the drain and gate. Okay, so the gain, from the gate to drain, this amplification is minus GMRL prime, because you can take this VGS down the denominator of V naught. Okay, so it becomes the gain, right? I mean this. Well, this part is the gain. Okay, this part is the gain. This is VDS. So, well, what you can do is just write VDS by VGS is the gain. Let's call this gain as AGD. From gate to drain, AGD is equal to minus GM R prime. So that's the gain from gate to drain. Okay. So this is the same value as in the midband. So the current IGD can now be found as, so IGD is the current in the capacitance CGD, right? And so you know that at this node, the gate node, the AC voltage is VGS, okay? And at this node, the voltage is V naught or VDS. So the difference of VGS minus V naught divided by 1 over omega C. So omega can be written in terms of the complex frequency S. Okay, S is j omega basically. So S is the complex frequency variable. So dividing it by 1 over SCGD. So the current can be written as just by Ohm's law. This is voltage divided by the impedance. Impedance is SCGD, which comes in the numerator then. Okay. So IGD, if you plug the expression for V naught from this equation, this becomes SGD VGS plus GM RL prime VGS. Okay, so you can take VGS out. So you can see this because the MOSFET from the gate side only knows this capacitance through the current IGD, because it's taking the current, this small capacitance is taking the current IGD, okay, inside of it. Okay, I mean from the gate, we were not used to consider the current into the gate terminal, but now since we are considering the internal capacitance of the MOSFET is drawing that current, and that current is being derived by the capacitance. Okay, so now you see, if you can replace this by call it an equivalent capacitance, C equivalent, you can bring this expression. I mean this becomes S C equivalent VGS, right? S equivalent VGS. You can bring this C equivalent in parallel with CGS. So this is going to turn the circuit into a single pole RC circuit, a low pass configuration circuit at the input of the MOSFET, just like this. And we can very easily develop the transfer function there, right? I mean this is going to be your R signal prime, and this R signal prime is going to have the same value which is written over here, the same resistance, Thevenin resistance, and then there will be a parallel combination of CGS in parallel with C. Basically, in parallel, you just add it up. So C equivalent is this expression. So now the left hand side of the circuit, that's about XX prime. So around this point, XX prime, it knows that existence of CGD only through the current IGD, because the MOSFET is driving the current, and that's due to the consideration of CGD. Therefore, we can replace CGD by an equivalent capacitance, C equivalent, between the gate and the ground. So as long as C equivalent draws the current equivalent to IGD, well, this can. So this is the expression. So SC equivalent VGS is this expression. This is the C equivalent. So we can very well. I mean we can. From this valid approximation, we can bring this C equivalent in parallel with CGS, and then we have more simplification. Circuit looks like this. So you see again the input circuit. The input circuit is your single pole RC circuit. So it's like this: R signal parallel with the equivalent capacitance C equivalent plus CGS. That's it. Okay. So the transfer function can be readily written as in the form of. I mean, if you're going to drive the transfer function, this is your input voltage, and this is your output voltage. Then, in terms of V naught by V in, the transfer function can be shown as, well, we can write this as 1 plus 1 plus in terms of normalized values S over omega, okay, where this omega is the time constant. Time constant is 1 over RC, okay, where omega is 1 over RC, which is in this case is C equivalent plus CGS. So C equivalent does enable us to simplify the equivalent circuit at the input side, so which is shown in the figure below. Okay, so C equivalent is involving all the transcondensals gain and RL prime, CGD, which is coming from the previous expression by putting V naught over here, and then bringing for this for VGS. So you take the difference VGS minus V naught, just take the VGS out of this expression, okay, and then you have the basically you have derived the gain from gate to drain, okay. So the output voltage VGS of this circuit can be expressed in this form, that is VGS is written as RG. So V signal can be brought to the other side for the gain expression. This becomes basically this is the input voltage which is available. Okay, so this is RG plus R signal into 1 over 1 plus S over omega naught. Note the expression is very similar to the single pole RC circuit. So omega naught is the corner frequency. You see, by corner frequency, it means that that's exactly the frequency where the response falls off to 3 dB. Okay, so in this expression, if S becomes equal to omega naught, okay, this is omega naught, this is omega naught. So if S becomes equal to omega naught, then this expression becomes 1 over 2. Okay, so that's the point at which if this is the magnitude response, then it becomes 1 over under root 2. So the response actually, where this is the point where the response falls off to 3 dBs. Okay, so omega naught is 1 over sin R signal prime, and R signal prime is given as parallel combination of R signal to RG. Okay, parallel combination of R signal by RG. So omega naught is the corner frequencies, where C in is the combination of CGS and C equivalent. So it's CGS plus C equivalent. Just plug in the values of C equivalent, that is CGD 1 plus GMR prime. So R signal prime is R signal parallel with RG. So RG is normally much greater than R signal. So that an approximation will be written as such. This is just the source resistance, the output source resistance. So the expression for the high frequency gain of CS amplifier becomes, if you simplify, you use this expression, use the first two expressions. These are the first two expressions, and what you can do is just plug in for. So you have over here. You just bring for VGS. For VGS, this is simply this becomes V naught over minus GMRL. So this becomes V naught over. You can just put the expression for VGS from here to there, okay, and you can bring V naught in this expression. Then the ratio of V naught by free V signal is of this form, okay. So it's again low frequency. It's in the form of the response is low frequency response, because as S is going to I'm sorry, it's the high frequency response. As it's going to increase, this is for the complete common source amplifier voltage gain. So as S is going to increase, the voltage gain is going to drop. Okay, you can see from this expression, as S is going to infinity, the voltage gain is going to drop, and that is what is expected of it. So this can be expressed in the form of V naught by V in AM, and AM is the midband gain, which was independent of the frequency, which we have derived at the start of this video. So this is independent. This is the voltage gain independent of the frequency. So this part is independent of frequency, right? So omega h is the corner frequency, written as 1 over C in R signal prime, and in hertz you can divide this by 2 pi. You can bring 2 pi in the denominator. So this is also, for fh being much greater than fl, this is also the 3 dB bandwidth of it's a 3 dB bandwidth of your amplifier. Okay, so as S approaches to infinity, the response is going to drop. Okay, so the response is going to drop. So it's like a low pass response if you consider it from the mid band. If you're looking at it from the mid band all the way up to fh and beyond, then as S is increasing, the response is going to fall off. So we thus see that the high frequency response will be that of the low pass network with a 3 dB frequency FH, determined by the time constant C in R prime signal. So the figure below shows the sketch of the magnitude of the high frequency gain. So this is the frequency gain, and you can see the dependence of the gain, voltage gain on the frequency. Okay, so since this is a single RC pole circuit, single pole RC circuit, you're going to have minus 20 dBs per decade. If there are two poles, then it becomes minus 40 dBs, let's say. Okay, I mean, if there is a if you have, for example, order n is 1, but if it increases to twice, for example, if n becomes 2, then the roll-off becomes minus 40 dBs. Okay, so this figure shows the frequency plot, which is that of the low pass single time constant circuit. And so before leaving this discussion, let's make there's a number of observations. The first is that the upper 3 dB frequency is determined by the interaction of R signal and Cin. Okay, why? Because the corner frequency is in terms of Cin and R signal. So since the bias resistance is usually very large, so it can be neglected, thus resulting the R signal prime to be the output signal source only. So the resistance of the signal source, so R signal can be approximately written as in terms of R signal only. Okay, because RG is very large. So it follows that a large value of R signal will cause FH to be lowered. So what it means is that if you have which you see over here, if R signal is large, then the corner frequency, if R signal is large, the corner frequency is going to be small, right? It has an inverse dependence. So this 3 dB frequency is going to start earlier. So it might shift FH down somewhere so that it decreases the 3 dB bandwidth as well. So you don't want to have the output signal source resistance to be large enough, okay? Because large value of R signal is going to cause the FH to be lowered, which implies that the 3 dB bandwidth is going to be small. It also implies that the 3 dB bandwidth is going to be small. So this is going to decrease as well with R signal increasing. That's the first observation on the corner frequency. Then the second is the total input capacitance Cin is usually dominated by C equivalent, which in turn is made of multiplication effect that CGD undergoes. So if you look at the expression of Cin, okay, it consists of CGS in parallel with C equivalent, and C equivalent has the multiplication factor of CGD, which means CGD is very prominent and is very dominant in describing the it has an influence on the frequency response of the amplifier overall. So to solve the CGDs, usually very small capacitance, its effect on the amplifier frequency response can be very significant as a result of the multiplication factor by a factor of 1 plus GMRL prime, which is approximately equal to the midband gain of the amplifier. So you see the midband gain is GM, this is RL prime, so this factor is RL prime. So basically your GM RL prime, I mean if RG is much larger than R signal, then this is primarily your midband gain, and your CGD capacitance is just multiplying basically your midband gain. If GMRL prime is much greater than 1, then this is primarily the midband gain, right? So although CGD is small, but if midband gain is huge, okay, then this capacitance, this term is very much effective in influencing your frequency response, okay? Although CGD is small, but it is being multiplied by the midband gain, so which can have a very prominent effect on the frequency response. Third is the multiplication effect that CGD undergoes comes about it because it is connected between two nodes whose voltages are related by a large negative gain minus GMRL prime. And if you recall this common source configuration, although it results in phase reversal due to the negative sign of the input and output voltages, but I mean the output voltage is 180 degree out of phase of input, It also gives a very huge gain. Other than that, I mean, for example, the source follower or the common drain configuration has a gain of normally close to unity or like 90% or 87%. But common source is the only configuration besides common gate and common drain which is going to give you a very large midband gain. So this midband gain is being multiplied by CGD. Okay, so the multiplication effect the CGD undergoes comes about it. It is connected between the two nodes and the voltages are related by a large negative gain. So this effect is known as the Miller effect. So and 1 plus GMRL prime is known as the Miller's multiplier. Okay, so this basically makes the effect of CGD, which is otherwise very small capacitance, but since CGD gets multiplied by 1 plus GMRL, which is about the GMRL prime, which is the midband gain. Okay, so this has a very pronounced effect. I mean, this has a very pronounced effect on the frequency response, overall frequency response. Okay, this is the midband gain. So, so there's a large gain. This effect is known as Miller effect, and 1 plus GMRL prime is a Miller multiplier. So this is Miller's multiplier MM. Okay, this is the Miller's multiplier. So it is the Miller effect that causes CS amplifier to have a large total input capacitance Cin and hence a low FH prime. So you see again the effect is to, because you're in the corner frequency you have the Cn. So for large Cn, omega h is going to drop again. Omega h is the corner frequency. So due to the Miller effect, which is seen because the midband gain is multiplying CGD. Okay, that's the Miller effect. So since Cn is huge, although CGD is small, but CGD when multiplied by the midband gain becomes a large quantity. Okay, so that results in Cn becoming large, and if Cn is large, then your 3 dB frequency FH becomes small, which results in lowering the 3 dB bandwidth. Okay, the bandwidth becomes small. So this Miller effect reduces your 3 dB bandwidth. So to extend the high frequency response of a MOSFET amplifier, we have to find the configuration in which this Miller effect is absent or at least reduced. Okay, so we have to find some configurations how this can be reduced so that we can reinstate the large 3 dB bandwidth. Okay, so the above analysis results in a single pole response is a simplified one. So specifically, it is based on neglecting IGD relative to GM/VGS prime, an assumption that applies well at frequencies not much higher than FH prime. Okay, so it's again a single pole circuit. So that's why you're having minus 20 dBs per decade, and it's a very simplified circuit analysis. We ignored, we neglected IGD, okay, and because you can do that in the vicinity of FH, but for the frequencies that are not very higher than FH, CGD has to be ignored. You see what happens around FH. If F is much greater than FH, then CGD is there, but around FH, when F is around approximately equal to FH, then you have to ignore this capacitance. You have to ignore this capacitance, therefore making IGD equal to 0. And primarily what you are doing is you are reducing the circuit to the midband regime circuit, in which the internal capacitances of the MOSFET can be ignored. Okay, so but around FH you end up in a very straightforward single pole RC circuit like this. Okay, so the transfer function is again a low pass transfer function, and omega h is or FH is the corner frequency. Okay, so the above analysis resulting in a single pole response simplified one. Specifically, it is based on neglecting IGT relative to GM/VGS prime, and this is an assumption that applies well at frequencies not much higher than FH prime. So we are around FH prime where we have this single pole RC response. Okay, this is example 4.12, I guess, from your course text, and this example says find the midband gain AM and the upper 3 dB frequency FH of a CS amplifier fed with a signal source having an internal resistance R signal. So R signal is given 100 Ks. The amplifier has the biasing gain resistance of 4.7 megas. You can see this RG is much greater than R signal. So, well, basically in this expression similar just reduces to 1. Okay, becomes 1 for RG, much greater than R signal. Okay, so RD is the same as the load resistance, which is 15 K. Transcript gain is given 1. R0 is the small signal output resistance, drain and source of the transistor. CGS is given as 1 picofarad, and CGD is again is a fraction of picofarad, 0.4, 40%, 4.4 picofarads. So the midband gain, well, this part is almost unity, so you don't need to consider about that. GM is 1, and RL prime consists of basically the parallel combination of R0, RD, RL. So R0 is 150, RD, RL are the same. Okay, so parallel combination is going to give you the smallest of all three, that is 7.14 kilos. If you solve that, then GM RL prime for unity gain is 7.14 volts. Okay, so that's the voltage gain. That's the voltage gain. So AM is about. I mean, it's not going to be too different because this factor is you can neglect this factor basically. I mean, this is 1. So the equivalent capacitance is found as you have to multiply CGD with the Miller's multiplier, 1 plus GM RL prime. RL prime, you know what is RL prime, is 7.14 kilos. And okay, so adding 1 is okay, not much of, but 1 plus 7.14 is the Miller multiplier, multiplied by 0.4 is to see equivalent capacitance. The total input capacitance around FH is now given as CGS plus the equivalent. CGS is given as 1 picofarads, so this is 4.26 picofarads. So the corner frequency is C in multiplied by R in. Okay, C in and R, you can say this R signal prime, and this again is since RG is much large, you can neglect that. This will be of the order of R signal, so this is 0.1 parallel combination of 4.7, and this comes out to be 382 kilohertz. Okay, so this is your corner frequency at which the response falls off minus 3 dB of the midband gain. Okay, this is the frequency where the voltage gain falls off 3 dB of the midband gain. Also, you must notice that if you have an increased C, then FH is small. That is due to this Miller's multiplier effect. This is the Miller's multiplier. Okay, so although CGD is small, although CGD is given as 0.4 picofarads, but this becomes equal to 3.26 picofarads. So because of the large common source midband gain, that Miller multiplier is increasing the C equivalent, which comes across CGS in the equivalent circuit, therefore making it to 4.26 picofarads. So you see how it had transformed from 0.4 to 4.26 picofarads, primarily due to the multiplication of Miller's multiplier. Okay, CGS is also a small capacitance, it's also a MOSFET small capacitance, but then this has a very pronounced effect on the frequency response also, that it lowers the bandwidth. The bandwidth has been lowered, right? FH is 382 kilohertz, but if we wouldn't have this Miller's multiplier over here, and CGS again, I mean, adding CGS would have been in such a configuration. Adding CGS would produce a CN equal to 1.4 picofarads, and your FH could be much higher. Okay, the FH could be 1.4 picofarads. It's like multiplying your bandwidth with 4 times. It would have increased the bandwidth 4 times. Okay, so the Miller effect is very much pronounced in reducing your 3 dB bandwidth. Okay, so that's about the high frequency response of the common source amplifier.